According to the general theory of relativity, gravity is not a force in the traditional sense. In fact, what we perceive as gravity can be understood as an effect of curved spacetime rather than a physical field acting at a distance. A key insight leading to this idea came from a thought experiment often described as one of Einstein's happiest thoughts. He imagined a person falling from the roof of a house. During the fall, that individual would feel completely weightless. Any object released would either remain at rest relative to them or move uniformly. From their perspective, the situation would be indistinguishable from floating freely in deep space, far from any massive bodies. In such a scenario, a person drifting in space at constant velocity experiences no forces and is considered an inertial observer. The laws of physics behave identically in all inertial frames, and no experiment conducted internally could distinguish one inertial frame from another. Einstein's profound leap was recognizing that these two situations, free fall near Earth and uniform motion in deep space, are not merely similar, but physically equivalent. This idea is known as the equivalence principle. It implies that a freely falling observer is not experiencing gravity in the conventional sense and is, in fact, in an inertial frame. At first glance, this seems counterintuitive. After all, a falling object near Earth clearly accelerates at approximately 9.8 m/s2. However, the equivalence principle emphasizes the observer's experience. If no force is felt, the frame is effectively inertial. Consider a spacecraft passing near a massive object like a planet. From an external viewpoint, its path appears curved as it accelerates toward the planet. Yet inside the spacecraft, the occupant feels no force and remains weightless throughout the journey. The onboard experience remains consistent, suggesting that the observer continues along an inertial path. This leads to a fundamental conclusion. Objects in free fall move along straight paths, not in ordinary space, but in spacetime. However, spacetime itself is curved by mass and energy. As a result, these straight paths, known as geodesics, may appear curved when viewed externally. An analogy can help clarify this. Aircraft flying long distances follow the shortest path between 2 points on Earth's curved surface. These routes may look curved on a map, but are actually the most direct paths, geodesics, on a curved surface. Similarly, objects in spacetime follow geodesics shaped by curvature. Another illustration involves two people starting at different points along the equator and walking due north. Although each moves straight ahead locally, their paths converge at the North Pole. It may appear as though a force is drawing them together, but in reality, the convergence results from the curvature of the surface. In the same way, gravity emerges not from a force but from the geometry of spacetime. Massive objects cause spacetime to curve, and this curvature dictates how objects move. In essence, matter tells spacetime how to curve, and spacetime tells matter how to move. Now consider the opposite situation: acceleration in deep space. If a spacecraft accelerates upward at 9.8 m/s2, objects inside appear to fall toward the floor, and the occupant feels a force identical to gravity. This demonstrates that being at rest on Earth's surface is physically equivalent to accelerating in space. From the perspective of general relativity, a person standing on Earth is not at rest in an inertial frame. Instead, they are accelerating upward, prevented from following their natural geodesic path by the ground beneath them. The sensation of weight arises from this upward acceleration caused by contact forces. This reinterpretation resolves a long-standing mystery in classical physics. why all objects fall at the same rate. In Newtonian physics, gravitational mass and inertial mass are treated as distinct yet experimentally identical quantities. In general relativity, this equivalence is no longer mysterious objects in free fall are simply following the same geodesic paths, independent of their mass. One of the most important predictions of this framework is that light should bend in a gravitational field. If acceleration can deflect light, then by equivalence, so should gravity. This was confirmed in 1919 when observations during a total solar eclipse showed that starlight passing near the Sun was deflected exactly as predicted. General relativity has since passed numerous experimental tests and remains one of the most successful theories in physics. Yet, it continues to challenge our intuition. Ultimately, what we call gravity is not a force pulling objects together, but the manifestation of curved spacetime guiding their motion. Objects in free fall are not accelerating, they are simply following the straightest possible paths in a curved universe.